Hi McGrath, how are you? I hope you're all doing well. I apologise that this is not our normal live lesson. I know we always have a live lesson on a Wednesday. I suppose number one, Virgin Media have put a sign through the door saying that they've workers in our lodge and the Wi-Fi could be cut off. So I'm worried I won't be able to do it live. So I'm doing it here on Tuesday night. And the second reason is that our order from this crowd here is arriving in the morning down to the school. So there's a truck coming with all our new equipment for our brand new lab. So I have organised to be in with the transition years down in the school tomorrow so that it's all there and set up for you to use when we return to the lab, because as we know, we got stuck in the classroom for one of our science classes all year, but all this equipment here is going to mean that we'll have the lab every day for science for the rest of the year and for next year as well. So so I apologise about the video. I did want to talk to you before the break, but not to worry, we'll have loads of time together to get through this course after the Easter holidays. And the only thing I want to do today really is just to chat through some of these questions here that I gave you yesterday, Tuesday. I also want to just remind you, and I'll do that now, of this. I want you to keep thinking about this. So you have no work for the break. You have no work. I don't think you should be doing any work over the break. The iPad and all should be going under the stairs, and you should be taking 2 weeks away from the screens as much as possible, and enjoying your holidays, because I know you haven't been in school, but you have worked hard. So I want you well rested for the last 5 or 6 weeks. So have nice 2 weeks off. But if you're watching television or you're reading or something like that, and something triggers your imagination, something experiment you might like to try in physics, chemistry, biology, jot it down, and we'll chat about that when we come back. And we're going to try and enter this SciFest competition, and then we're going to start talking about BT Young Scientists for next year as well. So that's the only thing I want you to do. Have a think about SciFest, your idea. If you think there's someone in the class who you might like to work with, shoot them an email or a WhatsApp or something, and try and set up your SciFest experiment. So only thing I want to do today is these questions here. Just go through some of the answers for density, speed, and acceleration. So if we think of density, straight out of the notes, so it's at the top of this same page, you would have found that definition. So you can do it two ways. You can say that density is mass over volume, or you can say density is the mass in a given volume. Okay, so definition up top of the page. So you have two. Make sure you're correcting these as you go along, because these are kind of questions that are going to be on your exam. I've already done that. The formula for calculating density is here. So density is equal to mass over volume. The units we use for density are grams per centimetres cubed. Again, that's up in the notes. Why does oil float on water? So why does oil float on water? So if we go back up to the top, we did that exact example up here. I'll show you now. Okay, oil floats on water as it is less dense than water, even though you wouldn't really think it is, but it is. So oil is less dense than water. Okay. Which liquid, X or Y, has the greatest density? X or Y. So which liquid has the greater density? Remember, look, if the wax block is the same, so which liquid is going to be more dense? Remember, it floats if it's less dense. So the object floats if it's less dense. You think if you're in the Dead Sea, which one is more dense? It's going to be X, isn't it? If you go to the Dead Sea, because it's really, really, really salty, its density is increased, which means you float in it. Okay. A student finds a rock on his way to school. In the lab, he finds the rock is 22 centimetres cubed. Volume is here. The mass is 66. Better get my calculator ready for these. I can do them for you. Okay, so we have our mass divided by our volume. So it's going to be 66 divided by, what's our volume? 22. So 66 divided by 22 is equal to 3 grams per centimeters cubed. There's our density. If a liquid, so again on this one they're giving us a mass and they're giving us a volume and they're asking us to find the density. So what we're going to do is we're going to have our mass, which is 30, divided by our density, which is 35. So just doing this with my calculator as we go along. And it works out as a decimal, so it works out as 0.86 grams per centimeter cube. But always this formula here, density is equal to mass divided by volume if you're going to calculate density. Okay, calculate the density of a rectangular block of wood that has a mass, okay, of 90, and the measurements, so they want us to find the volume. To define the volume of a rectangular block, which we did last week, we're going to have to find that first. So to find the volume, we do 5 by 3 by 3, which is equal to 5 3s are 15, is equal to 45 centimeters cubed. So now we have worked out what the volume is. So then we can calculate the density, same formula. Sorry, I haven't scrolled down. So what I've done there is I've multiplied length by width by height to get the volume. Here's the volume. And then I do the same formula, density equals mass, which is 90, over the volume, which is 45. So our density is going to be equal to 2 grams per centimeter cubed. 43. A ring was weighed and found to be 54 grams. Right, they're giving us a mass. The volume is 6 centimeters cubed. Calculate the density of the ring. So again, we're same formula again. Density, so our keep doing that. Density is equal to mass, 54 over volume, which is 6. So our answer is going to be 54, by the way, 6 is going to be 9 grams per centimeter cubed. And which one does that work out at? Okay, we can see it there. 9 grams. So the answer is copper. The answer is going to be copper. Okay, over to the second one. Speed. Okay. So remember, we have all these definitions. They're all up here in the notes. There's our speed one there. So distance, it travels in a particular time. So the speed definitions, I'm just going to show you. We have all these in here. There it is there. Distance traveled in a particular time. Okay. So let's go over to our speed question. Okay. Just zoom in. So speed is distance traveled in a unit of time. So how far you get in a particular time. Okay, there's a bit of a lag there and this in the screen. Okay, what are the units of speed then? So what are the units of speed? Well, we have a few of them, haven't we? We have meters per second. We have kilometers per hour. There are units of speed. Now, velocity is a step up. The velocity definition is speed in a given direction. So the difference is, if we say 40 kilometers per hour, we could still say that. We could still say 40 kilometers per hour. That's just a speed. But I would have to write it beside it a direction. 40 kilometers per hour north. That's the difference in speed and velocity. So remember this calculation that we were that if we wanted to work out, we have this triangle DST. So I can work out using this formula here. I can do, if I want to work out the distance, it's going to be speed multiplied by time. If I want to work out the speed, it's going to be distance divided by time. If I want to work out the time, it's going to be distance divided by speed. So there's my 3 formulas that I can pull out of that triangle. So they want us to find, in this question, number 47, they want us to find what is the speed. So we're looking for the speed. we're going to be using the speed formula here, which is distance divided by time. So it's going to be speed, distance is going to be 49 meters, 49, divided by 2.4. So I'll just do that on my calculator, 49 divided by 2.4, which is equal to 20.4. So 20.4 meters per second. That is going to be the speed. Which has a greater speed? This is 48. A ball rolling down a 3.4 meter hill in 6 seconds, or a fish swimming upstream and covering 5.4 meters in 0.4 seconds. We have to do two speed calculations here. So what we do is we do our ball rolling down a hill first. So for the first one, the ball rolling down a hill, speed is equal to distance 3.4 divided by 6. So 3.4 divided by 6, which is 0.57. So our first one is going to be 0.57 meters per second. There's our first speed. Our second one is the fish swimming upstream. The fish swimming upstream covers 5.4 meters divided by our time. How long did it take? 0.4 minutes. But we have to be careful there. 0.4 minutes. So less than half a minute. Remember this over on the left there. It's in seconds. So what would 0.4 of a minute be? It's going to be 24 seconds. So we can't put down 0.4. We have to put in the seconds. So the conversion is 24. So 5.4 divided by 24, which is equal to 0.225 meters per second. So which one is going to be faster? Is that the question? Which is the greater speed is going to be our ball rolling down a hill. Is going to be faster. The mistake people make there is they put in 0.4, but that is not in seconds. So you think, well, if it was 0.5, it'd be handy because it'd be 30 seconds. Half a minute is 30 seconds. But this is 0.4. So we multiply 0.4 by 60, and it gives us 24. How long does a horse take to walk 6 kilometers at a speed of 20 meters per second? Okay, how long? The question there is how long. So we're interested in time in this case. So it's going to be distance divided by speed. So time is going to be, well, we're going to meters per second here. So 6 kilometers is how many meters? Kilo, 1,000. So it's going to be 6,000 meters divided by 20 meters per second. So it's going to be 6,000 divided by 20, which is equal to 300 seconds. Like that. Okay. If Dungarvan Shopping Centre is 300 meters long and you walk at a pace of 1.3 meters per second, and again, here's my question. How long? I'm dealing again with time. So time is equal to distance divided by speed. So our distance, so we're looking at time again. Distance is 300 divided by our speed, which is 1.3. So 300 divided by 1.3 is going to be 231 seconds. And you can convert that to minutes. It doesn't ask you to, but you can convert that to minutes. You know that 60 seconds in a minute. So you could work that out in minutes and seconds if you want, but it does not ask you to do that. 51. If my toy train in class can move at a speed of 0.04 meters per second, they're giving us a speed. How long will it take to move? So we're going to how long again. We're still dealing with time. Time is equal to distance divided by speed. So it's going to be 5 divided by 0.04. So 5 divided by 0.04 is going to be 125 seconds. Okay. Same, I'm using that formula all the time. Distance divided by speed every time. Okay. You arrive in my class 45 seconds after leaving maths, which is 90 meters away. How fast? So how fast is what we're looking for there? How fast, which is the speed. So we're dealing with the speed one again. Distance divided by time. So speed is equal to distance, which is 90 meters, divided by seconds, which is 45, which is equal to 2 meters per second. Okay, so again, I'm using all these formulas. If they ask me how far or what distance, I'm using my distance formula. If they ask me how fast you were going, what speed you were going, I'm using my speed formula. And if they say how long does something take or what time, I'm using my time formula. Any of those three formulas will answer all these types of questions for you. How far can you get away from your little brother with a squirt gun filled with paint? So how far? How far? Straight away I know the question is distance. I know I'm going to be using this formula here. Speed multiplied by time. How far? Oh, sorry, how far? How far? Distance formula. Can you get away from your little brother with a squirt gun filled with paint? Squirt gun filled with paint, that'd be dreadful, wouldn't it? If you can travel 3 meters per second, so it's going to be distance I'm looking for. Speed by time, what's my speed? 3 meters per second. And you have 15 seconds. Okay, so that was going to 3 by 15, which gives you 45, and it's a distance, so it's going to be meters. All right, all these are in the video. If you want to go back and take a look, or if you have any questions at all, email me anytime, and I will go through it, or I'll stick an audio note in to explain what the issue is, or what make it a bit clearer for you. Once you can do a few of them, you kind of most people will be away in a hack. Okay, now. Sorry, I didn't scroll down there. I was doing it on the iPad. But there's your solutions in here. So you see them? You can pause the video if you need to catch up on one or two of those. Okay. Right. We're going down here to our distance time graph. And you see these graphs here. So this is a guy who's on a bike, or a girl who's on a bike. And she starts off down here in the bottom corner. So she hasn't gone anywhere. 0 distance and 0 time. And what happens is after 20 minutes, she's 2 kilometers from home. After 40 minutes, 4 kilometers from home. After an hour, might go up here. So this is the distance on the left, and across the bottom is how long she was out cycling. So you can see you can kind of get a feeling what happened. This is kind of as time goes by, she's getting further away from home. Then there's a stop. Not getting any further. Time's still going by. Stops for a Kit Kat or something. And then decides to return back to home. So it's like a cycle. So cycling on the slope, and then when the line's flat, not cycling at all. Okay, how far had Margaret cycled after 30 minutes? Right, so have a look at our graph. Well, okay, well here we have 20 minutes here, and we have 40 minutes here. So somewhere in the middle here is going to be 30 minutes. So what we do is we say, right, let's see where Margaret is after 30 minutes. Up as far as the graph, and in, and that's how far there. 6 kilometers. It's a bit of a lag, but it should be coming up for you now in a second. So the answer is going to be 6 kilometers. After 60 minutes, just makes it slightly smaller so we can fit the graph in. After 60 minutes, Margaret stopped for a rest. So you can see there, here's 60 minutes here. And you can see there's a stop there for a rest. For how many minutes did she rest for? Okay, well after 60 minutes, that's when she stopped. But when did she start going again? When did she start making the journey home? Somewhere here, wasn't it, when she started going home? So, well, if she stopped after 60 minutes and started again at 80 minutes, she was stopped for 20 minutes. How far did Michael cycle on total in her journey? Well, if we look at that curve, and what we're doing is now at this point, we're focusing on this part of the line here. And we say, well, did she go 2k? Yep, she did go 2k. 4 kilometers, yes. 6, 8, 10, yep, still cycling at 10 kilometers. And 12 kilometers. She doesn't go 14 kilometers. The line doesn't go up as far as here. The line would have to keep going up like that for 14 kilometers. So she went 12 kilometers, and then this part she was stopped, and then she went all the way back to the start again. So how far did she go? Well, if she went from the bottom right up to the top here was 12 kilometers. Here she wasn't moving at all, and then a cycle all the way back is another 12 kilometers. So her total cycle is 12 and 12 is 24 kilometers. What was Margaret's average speed for the first 60 minutes? So how fast was she going? Remember, to find the speed, we have speed is distance divided by time. So if we pick any distance or any time, right? So say we choose 8 kilometers. So there's 8 kilometers. There's our distance. And we say, right, well, distance, that's a far. And how long did it take her to go 8 kilometers? So let's go across to the line and down. It took 40 minutes. So if we have 8 kilometers in 40 minutes, you have to be careful. Remember, it's either meters per second or kilometers per hour. So we can't put 8 over 40. We're going to have, because it's 40 minutes, so 4 over 6, which is 2/3 of an hour. So it's going to be 8 over, if we go back to a decimal, 0.66. That's 2/3 of an hour. 8 divided by 0.66, which is going to be 12.12 kilometers per hour. Okay, so 12.12 kilometers per hour. Last one. What was Margaret's average speed for the journey home? Okay, it looks kind of symmetrical. It should be something similar. So we say, right, well, we say if we're going from this speed here, so at 12 kilometers, if we take this distance, and distance over, so speed is distance over time. So if we say, right, well, 12 kilometers, and we choose a different distance as well. So we're going between 80 and 100. So we say, well, how far was she at 12 kilometers? It's going to go from 12 to 10. So it's going to be, our distance is going to be 2. So distance is going to be 2 because we're going from 12 to 10. Over how long did it take? So distance over how long did it take to go from 12 to 10? It took, where's 10? 10 is here. So about 85. So somewhere in the middle there, do you see the arrow going up and down? Somewhere between 80 and 90. So about 85. So it's going to take about 5. So what's that? 5 minutes. So 1 over, I'll just do that as a calculation. So 5 divided by 60, which is 0.08. So 2 over 0.08. Let me just do that in the calculator. So 2 divided by 0.08. Nope. 0.8, which is faster, is 25 kilometers per hour. And we can do that for any speed. I'm just going to get rid of some of this just to show you that, just to show you that last one again here, right? Just show you this last one. Just get rid of that. I'm just going to get rid of this for a second. There's a lot of marks on it at this point because I'm showing you the different parts. So just get rid of this, but you can see it again in the video if you need any of these marks, right? So we're looking for her average speed on the way home. So we're looking for a distance divided by a time. Right. So if we take the whole distance here between where she started off after her rest and got home, what's the distance going to be? Well, we know the distance is going to be 12. So get rid of that for a second. So we know we're looking for speed is equal to distance divided by time. So we know from our graph that our distance all the way home is going to be 12. How long did it take her to get that distance? So she went from 80 to 120. So what's the difference between those two? It's going to be 40. But we have to be careful because this is in kilometers and this is in minutes. So remember, we have to be in either kilometers per hour or meters per second. So there's two ways of doing this. I can either change that to meters, or I can change this to seconds. And since I've done it the other way, I'll do it the opposite way this time. So as opposed to 12 kilometers, kilo means 1,000. It's going to be 12,000 meters over 40. So if we go 12,000 divided by 40, which gives us way too much. 40 seconds. No, what am I doing? It's minutes in kilometers. I thought that I have to get an answer of 300 kilometers per hour. Saying, how am I getting an answer of 300 kilometers per hour? Go back for a second. Distance over time. So, and we're in minutes. So we're looking, what's the distance? Well, the distance is still going to be 12 kilometers. We worked that out already. That's in kilometers. Now, our time it took for that distance is going to be 40 seconds. So we think, right, 40 seconds. How much of a minute is that? How much of a minute is 40 seconds? It's going to be 0.66 of a minute, so 2/3 of a minute. If it was 20 seconds, it'd be 0.33 of a minute. If it was 30 seconds, it'd be 0.5 of a minute. So it's how much of a minute. And when we divide 12 divided by 0.66, it gives us 18.18 meters per second. Like that. Okay. Very good. Right, now let's go on a bit. We'll try and finish this off. I know it's taking quite a long time, but we're not far off now. Acceleration, right? So acceleration is the, straight off the notes up the top, is the change in speed in a given time. Okay, how is acceleration calculated? Remember, there's a formula. The units first off are meters per second squared. So speed is meters per second, acceleration is meters per second squared. It's calculated, right? So I'm going to do that. I'm going to space here. I'm going to the side. So we calculate acceleration. This is going to be handy for the calculations. Acceleration is change in speed over the time taken for the change. Okay, so the change in speed over the time, this is loading, time taken for that change. So I'll just zoom out so you can still see that. A cyclist accelerates from 0 to 8 in 3 seconds. So we calculate our acceleration. Remember, it's the change in speed. Well, it's gone from 0 to 8. So it's going to be 8. That's the difference between 0 and 8. Divided by, how long did it take? It took 3, didn't it? So we're going to have 8 divided by 3, which is 2.66. 2.66 meters per second squared. And like I said, I'd rather you were in the lab working out distance, speeds and times, and then calculating your acceleration based on your own walking and running and that kind of thing. But that's what we will do. I'm just getting the bit of theory out of the way. Okay, last couple. I'm just going to do a couple of these because they're all pretty much the same, using the same formula. So we just do 64 and 67, just so you're not watching this for ages and ages. A car advertisement states that a certain car can accelerate. You hear this all the time. The Bugatti Veyron goes from 0 to 70 in 7 seconds, like they say here. Find the acceleration. Okay, well, our acceleration A is the change in speed. So from rest, from nothing to 70. So 70 is our change in speed in 7 seconds. So it has an acceleration then of 10 meters per second squared. Okay, all these are the same idea. We'll do one more of these. A ball is dropped from top of a building. After 2 seconds, its speed is measured to be 19.6 meters per second. Okay, so acceleration again. The change in speed is going to be, because it was dropped from someone holding it, obviously, or rolled off the roof or something. 19.6 is our change in speed. Divided by how long did that change take is 2 seconds. And we're still in meters per second and seconds, so we don't have to do any conversions. So we're doing 19.6 divided by 2, which is 9.8 meters per second, and squared because of acceleration. All right, the very last thing I want to show you guys is these speed time graphs. So they're very like the last one, but the difference is that this axis on the left is speed, so how fast something is going, and this one here is time. So calculate the time to accelerate to a constant speed. So here's our constant speed here. You can see here that time is going by, but the speed is not going any higher. It's not going up, it's not going down. So that's what it means. So how long did it take this car to go to a constant speed? And the answer is here. So here's where the constant speed started. That spot there. And the answer is around about, is it? It's actually less. It's this one here. So it's going to be, it's not going to be 20 seconds, because 20 seconds would be here. So 5, 10. So it's going to be here at 15. So it's 15 seconds. You see how you can make this? You can assume that was actually on the 20, but it's actually on the 15. So it's before the 20. How long the train travelled at a constant speed? Okay, so it came to a constant speed of 15, and then it stopped being a constant speed at this point here, wherever this is. 82, 84, 86. 85 would be here, 90 be here, 95 would be here. So it stopped at a constant speed at 95. So it, at 15, it got to a constant speed, and it stayed there. Hold on, I didn't go down. Okay, there you are there. So here's our speed time graph here. So here's our speed of the train. So you can see there at that this train. I'm just going to get rid of some of these marks for a second because I haven't scrolled down enough for you to see it. There's a bit of a lag on the screen, so it looked like you could see it, but you obviously couldn't when I flick back. So we have a speed time graph here, right? So this over here, our speeds are all on this axis here, and our times are down the bottom. So if this is a train, what's happening is here, the train starts at the bottom corner and then accelerates really quick all the way up as far as here. Now the train doesn't stop then. The train stays at the same speed. So you can see over here, it's not getting faster, it's not getting slower, and then it starts to slow down. The train driver hits the brakes and brings the train back to zero. And what they're asking us in these questions, how long does it take to accelerate to a constant speed? What happens is that it started at zero and it accelerated, and around about here it got to a speed and didn't change again. So we were wondering, what is that point? I've actually already said this in the video, but you couldn't see it. I'm going down here, that point there, and it's not quite 20 minutes. It's not quite 20 seconds, it's about 15 seconds. So we say, well, that's going to be 5, that's going to be 10, it's going to be 15 seconds. Okay. The last one I was working on there before I managed to actually get you down to the page is how calculate how long the train travelled at that constant speed. Okay, well it got to a constant speed at 15 seconds, and it stayed at that constant speed until that point there. So we say, right, let's go to that point and go down to that point here, and that's going to be 95 seconds. So it stayed at the constant speed from 15 seconds to 95 seconds. You're saying, well, okay, well, what is the jump from 15 to 95? How long has that been? And the answer is going to be it stayed at that constant speed for 80 seconds. 95 minus 15. Calculate the constant speed of the train. So how fast was it going? How fast was it going at this speed here? Well, we know the constant speed of the train is this block here. I'll just get rid of those so we can see it. So we're looking at this part of the graph here. What is the constant speed of the train? We can say, well, this axis here, this bit down here, tells us speed. This axis here tells us speed, and we know then that all of this whole straight line here is at 90 meters per second. Okay, so I'm going to write 90 meters per second. That's the constant speed of the train. Last one then, calculate the acceleration of the train at the start of the journey. Right, so remember our formula for acceleration. I'm just going to put it down. Acceleration equals is the change in speed all over time taken for that change, like so. So what was the change in speed over how long did it take for that change? Right, so we say, right, well, the train started off at nothing. The train started off with no speed at all. So our change in speed, it goes from 0 up to 90 meters per second. So let's go back down and fill it in. So our change in speed is going to be 90 over. How long did that take? Well, okay, it got there. We worked it out earlier on. It took 15 seconds. So here's when it got to that. We go down, and it's 15 seconds. So we fill that in on our graph as well. So it's going to be 90 over 15, which is equal to 6 meters per second squared. 15, 30, 40, yes, it's 90 meters per second squared. Okay, so tricky kind of questions to end on, and we'll be doing lots more examples of those when we get back. As I said in Tuesday's video, we have we've a lot of practicals left to do. This is pretty much the last thing I need to do with you in theory. So we'll be doing practical, SciFest, all that kind of stuff when we go back. We've lots of lab stuff to be doing, and like I said, that's why today's class couldn't be live, because I'm down in school trying to get all that set up for you with the TYs and so on, and of course the internet's not working tomorrow apparently, so they say. Anyway, so I hope you all have a fabulous Easter. I'm looking forward to seeing you all again, and doing some really, really cool science experiments and getting out and doing some ecology out in the outdoors and playing with some chemicals. And I'm sure we'll have a very nice last term. In the meantime, though, you get the books away, get the iPad away, have a great Easter, get lots of rest, and I'll talk to you after the break. If you have any questions in the meantime, or ideas for Science SciFest, or you're not sure of those questions that I just went through there because they're difficult, and you want to know the answer before we go back, send me an email and I will get back to you as quick as I can. Mind yourselves. Take care. Bye-bye.